When we think of the age of dinosaurs, most of us picture massive beasts thundering across ancient landscapes, towering sauropods stretching their necks to reach the tallest trees, ferocious predators like Tyrannosaurus rex stalking through primeval forests. But what if I told you that some of the most incredible dinosaur-related creatures never set foot on land at all? Deep beneath the waves of ancient oceans, an entirely different world was taking shape. While their land-dwelling cousins were evolving into the giants we know and love, other reptilian lineages were making a bold evolutionary leap into the marine realm. These weren't just any ordinary sea creatures. These were some of the most sophisticated, powerful, and downright terrifying predators that ever ruled the waves. Over the next few minutes, I'm going to take you on a journey back in time to explore the hidden underwater empire that thrived alongside the famous terrestrial dinosaurs. We'll discover how these marine reptiles evolved from humble land-dwelling ancestors into apex predators perfectly adapted for life in the open ocean. You'll learn about the evolutionary arms race that drove these creatures to develop some of the most extreme adaptations in natural history. And by the end of this journey, you'll understand why these oceanic titans were every bit as remarkable as their land-based relatives. But here's what makes this story even more fascinating. While dinosaurs dominated the land for over 160 million years, these marine reptiles actually ruled the oceans for even longer. They survived multiple mass extinction events, adapted to changing climates, and evolved into forms so bizarre and specialized that they seem almost alien to us today. Some grew larger than modern blue whales, while others developed echolocation systems more sophisticated than dolphins. A few even evolved to give live birth in the open ocean, completely abandoning any connection to the land their ancestors once called home. This isn't just another story about prehistoric animals. This is the untold chapter of Earth's history that reveals how life found a way to conquer every corner of our planet's vast oceans. From the shallow coastal waters to the deepest ocean trenches, these marine reptiles carved out ecological niches that wouldn't be filled again until millions of years later. The story begins around 250 million years ago, in the aftermath of the greatest catastrophe our planet has ever experienced. The end Permian extinction had wiped out over 90% of all marine species, leaving the oceans eerily empty and ripe for colonization. On land, the first archosaurs were just beginning to diversify into the lineages that would eventually give rise to dinosaurs, crocodiles, and birds. But in the oceans, a different kind of evolutionary experiment was already underway. Picture the ancient coastlines of the early Triassic period. The world was hot, humid, and largely covered by a single massive ocean called Panthalassa. Along the shores of this primordial sea, small reptiles were making tentative forays into the marine environment. These weren't dramatic overnight transformations. Instead, they represented the beginning of a gradual evolutionary journey that would span millions of years and produce some of the most incredible creatures ever to inhabit our planet. At first, these early marine reptiles were modest in both size and ambition. They likely fed on fish, small crustaceans, and other marine invertebrates in shallow coastal waters. Their limbs were still clearly adapted for walking on land, and they probably returned to shore to lay their eggs. But even these humble beginnings contained the seeds of something extraordinary. The key to understanding this marine revolution lies in recognizing the incredible opportunities that awaited any reptile bold enough to venture into the water. The post-extinction oceans were like a vast, largely unexploited frontier. Food was abundant, competition was minimal, and the three-dimensional nature of the marine environment offered countless new ecological niches waiting to be filled. For reptiles that could successfully adapt to this aquatic lifestyle, the rewards were immense. But adaptation to marine life isn't simple. It requires fundamental changes to nearly every aspect of an animal's biology. Limbs must be modified for swimming rather than walking. Sensory systems need to function underwater. Respiratory systems must be capable of holding breath for extended periods. And perhaps most challenging of all, reproduction must somehow be managed in an environment where returning to land becomes increasingly difficult or impossible. Different groups of reptiles solved these challenges in remarkably different ways, leading to an explosion of marine diversity that would define ocean ecosystems for the next 180 million years. Some evolved into sleek, dolphin-like forms, perfectly streamlined for high-speed pursuit of prey. Others became massive, slow-moving giants that used their enormous size to dominate their marine territories. Still others developed bizarre feeding strategies that allowed them to exploit food sources no other predator could access. The first major group to make this transition were the ichthyosaurs, whose name literally means fish lizards. These remarkable animals represent one of the most dramatic examples of convergent evolution in the fossil record. Starting from typical land-dwelling reptiles, they evolved into creatures that looked almost identical to modern dolphins and sharks. Their limbs transformed into powerful flippers. Their bodies became torpedo-shaped for maximum hydrodynamic efficiency, and their tails developed the distinctive crescent shape that provides optimal thrust for high-speed swimming. But ichthyosaurs didn't stop at simply copying the basic body plan of fish. They pushed the boundaries of aquatic adaptation to extremes that even modern marine mammals haven't achieved. Some species developed the largest eyes of any known vertebrate, allowing them to hunt in the dim depths of the open ocean. Others evolved specialized feeding mechanisms that let them capture and process prey in ways that seem almost impossible for air-breathing reptiles. The fossil record reveals that ichthyosaurs achieved their remarkable adaptations with stunning speed. Within just a few million years of first entering the marine environment, they had already evolved into fully aquatic predators that never needed to return to land. This rapid evolutionary transformation suggests that the selective pressures favoring aquatic adaptations were incredibly strong during this period. As ichthyosaurs were perfecting their fish-like bodies, another group of marine reptiles was taking a completely different evolutionary approach. The plesiosaurs, whose name means near lizards, retained a more obviously reptilian appearance while developing their own unique solutions to the challenges of marine life. Instead of evolving the streamlined bodies of ichthyosaurs, plesiosaurs developed incredibly long necks and powerful paddle-like limbs that allowed them to maneuver through the water with surprising grace and precision. The diversity within the plesiosaur lineage is truly staggering. Some species evolved necks longer than their entire bodies, creating creatures that looked more like prehistoric lake monsters than conventional reptiles. These long-necked forms likely used stealth and surprise to capture prey, slowly approaching schools of fish or other marine animals before striking with lightning speed. Other plesiosaurs went in the opposite direction, evolving massive skulls and short, powerful necks that turned them into the marine equivalent of apex predators like Tyrannosaurus rex. What makes the plesiosaur story even more remarkable is how they solved the fundamental challenge of underwater locomotion. Unlike ichthyosaurs, which used their tails for propulsion just like fish and dolphins, plesiosaurs evolved a completely unique swimming style. They used their four large flippers in a coordinated flying motion underwater, essentially flying through the water in much the same way that modern sea turtles do today, but with far greater power and efficiency. This underwater flight system gave plesiosaurs incredible maneuverability, allowing them to make sharp turns and sudden direction changes that would have been impossible for the more streamlined ichthyosaurs. This advantage likely allowed plesiosaurs to exploit different hunting strategies and occupy ecological niches that their more fish-like contemporaries couldn't access. The third major group of marine reptiles took yet another evolutionary path that was perhaps the most audacious of all. The mosasaurs, whose name means lizard of the Meuse River, didn't appear until much later in the Mesozoic era, but when they finally made their entrance during the Cretaceous period, they did so with explosive success. These creatures evolved from relatively small, land-dwelling lizards into some of the most formidable predators the oceans have ever known. What makes mosasaurs particularly fascinating is that they represent the most recent major invasion of marine environments by reptiles. While ichthyosaurs and plesiosaurs had been perfecting their aquatic lifestyles for over 100 million years, mosasaurs burst onto the scene as evolutionary newcomers and quickly rose to dominate marine ecosystems worldwide. This late arrival makes their success story even more impressive, as they had to compete with well-established marine reptile lineages that had already carved out virtually every conceivable ecological niche. Mosasaurs solved the challenge of marine adaptation by becoming living submarines. Rather than developing the streamlined bodies of ichthyosaurs or the flying flippers of plesiosaurs, mosasaurs retained a more serpentine body plan while evolving powerful swimming adaptations. Their limbs transformed into paddle-shaped appendages, but their primary means of propulsion came from undulating their enormously long, vertically flattened tails through the water in a motion similar to modern sea snakes, but on a vastly larger scale. The diversity of mosasaur species that evolved during the Cretaceous period is nothing short of remarkable. Some remained relatively small and likely hunted fish and small marine creatures in coastal waters. Others grew to absolutely monstrous proportions, with the largest species reaching lengths that rivaled modern sperm whales. These giant mosasaurs possessed skulls over 2 meters long, filled with teeth designed for crushing and tearing through virtually any prey they encountered. But size wasn't the only weapon in the mosasaur arsenal. Many species developed specialized feeding adaptations that allowed them to exploit specific prey types with incredible efficiency. Some evolved crushing teeth, perfect for breaking through the shells of ammonites and other shelled marine creatures. Others developed needle-sharp teeth, ideal for catching slippery fish and squid. A few species even evolved massive, robust jaws that suggest they may have been capable of taking on other large marine reptiles as prey. The fossil evidence reveals that mosasaurs were incredibly successful predators that spread to oceans around the world with remarkable speed. Within just a few million years of their initial evolution, mosasaur fossils can be found on virtually every continent, suggesting that these marine reptiles were capable of crossing vast oceanic distances and establishing populations in widely separated seas. Perhaps most impressively, mosasaurs evolved sophisticated reproductive strategies that allowed them to give birth to live young in the open ocean. Fossil evidence shows that baby mosasaurs were born tail first, just like modern whales and dolphins, indicating that these ancient marine reptiles had solved one of the most challenging aspects of fully aquatic life. This reproductive adaptation meant that mosasaurs could complete their entire life cycles without ever needing to return to land, making them true masters of the marine environment. The evolutionary success of these 3 major groups of marine reptiles created ocean ecosystems that were more complex and dynamic than anything we see in modern seas. Imagine swimming in the ancient Tethys Sea during the height of the Mesozoic era. The waters would have been filled with ichthyosaurs of every conceivable size and shape, from dolphin-sized species chasing schools of fish to whale-sized giants patrolling the open ocean depths. Long-necked plesiosaurs would have moved through the water like underwater giraffes, their serpentine necks allowing them to probe into crevices and capture prey in ways no modern marine predator can match. In the depths below, massive short-necked plesiosaurs would have ruled as apex predators, their enormous flippers propelling them through the water with surprising speed and agility despite their intimidating size. And cutting through it all, the mosasaurs would have moved like living torpedoes, their powerful tails driving them forward as they pursued prey with relentless determination. These ancient oceans weren't just filled with large predators either. The fossil record reveals an incredible diversity of smaller marine reptiles that filled ecological roles similar to modern sea turtles, seals, and small whales. Some species evolved specialized filter-feeding mechanisms that allowed them to strain small organisms from the water. Others developed crushing teeth, perfect for eating shellfish and crustaceans. Still others became the marine equivalent of scavengers, cleaning up the remains left behind by larger predators. The complexity of these ancient marine ecosystems is perhaps best illustrated by examining the evolutionary arms race that developed between predators and their prey. As marine reptiles became larger and more sophisticated hunters, their prey species evolved increasingly elaborate defense mechanisms. Ammonites, the spiral-shelled cephalopods that were incredibly abundant during this period, developed thicker shells, more complex internal structures, and even defensive spines in response to predation pressure from marine reptiles. This predator-prey dynamic drove both groups to evolutionary extremes that seem almost impossible by modern standards. Some marine reptiles evolved bite forces that exceeded those of any living animal, while their prey developed shells and protective structures that were marvels of biological engineering. The result was an aquatic ecosystem where both hunters and hunted pushed the boundaries of what seemed biologically possible. The dominance of marine reptiles also had profound effects on the evolution of other marine life. Fish species during this period evolved in the shadow of these massive predators, developing new swimming techniques, schooling behaviors, and defensive adaptations that helped them survive in seas dominated by reptilian giants. Even microscopic marine organisms were affected, as the feeding activities of large marine reptiles created nutrient cycles and ecological relationships that shaped entire ocean ecosystems. What truly sets these ancient marine ecosystems apart from anything we see today is the sheer scale of evolutionary experimentation that took place beneath the waves. While terrestrial dinosaurs were certainly diverse, the marine reptiles achieved levels of morphological innovation that seem almost limitless. The three-dimensional nature of the ocean environment allowed for body plans and feeding strategies that would have been impossible on land. Consider the extraordinary range of sizes that evolved within each major group. Among the ichthyosaurs, species ranged from sleek, meter-long pursuit predators to absolute giants that dwarfed modern blue whales. The largest ichthyosaur species discovered so far stretched over 20 meters in length, with skulls alone measuring more than 3 meters from tip to tail. These massive creatures possessed eyes the size of dinner plates, suggesting they hunted in the deepest, darkest parts of ancient oceans where sunlight never penetrated. But even more remarkable than their size was the speed at which these giants could move through the water. Biomechanical studies of ichthyosaur fossils reveal that the largest species were capable of sustained swimming speeds that would put modern dolphins to shame. Their perfectly streamlined bodies, combined with incredibly powerful tail flukes, created living torpedoes that could traverse entire ocean basins in pursuit of prey or seasonal feeding grounds. The hunting strategies employed by these marine giants were as diverse as the creatures themselves. Some ichthyosaurs evolved into specialized deep-sea hunters, using their enormous eyes and sophisticated echolocation systems to track prey in the perpetual darkness of the ocean depths. Others became surface skimmers, using their speed and agility to chase flying fish and other surface-dwelling creatures. A few species even evolved into filter feeders, developing specialized jaw structures that allowed them to strain vast quantities of small organisms from the water like living baleen whales. Meanwhile, the plesiosaurs were pushing the boundaries of underwater maneuverability in ways that seemed to defy the laws of physics. The longest-necked species possessed necks containing over 70 individual vertebrae, creating appendages that could be manipulated with almost snake-like flexibility. These extraordinary necks weren't just for show. They represented sophisticated hunting tools that allowed plesiosaurs to capture prey in ways no other predator could match. Imagine watching a long-necked plesiosaur in action. Its massive body would remain motionless in the water column, suspended like a living island, while its impossibly long neck snaked through the surrounding water with predatory precision. Fish and other small marine creatures would have no warning of the approaching danger until it was far too late. The neck would strike with lightning speed, and prey would disappear into jaws lined with needle-sharp teeth designed for gripping slippery marine organisms. But not all plesiosaurs relied on stealth and surprise. The short-necked species, known as pliosaurs, evolved into some of the most formidable apex predators in Earth's history. These creatures combined the underwater flight capabilities of their long-necked relatives with skulls and jaws that rivaled those of the largest terrestrial predators. The most massive pliosaurs possessed heads over 2.5 meters long, filled with teeth the size of bananas and powered by jaw muscles that could generate bite forces exceeding 15 tons per square inch. These marine monsters didn't just prey on fish and smaller marine reptiles. Fossil evidence suggests that the largest pliosaurs regularly hunted other marine reptiles, including their own plesiosaur relatives and even smaller ichthyosaurs. Bite marks found on ichthyosaur fossils match perfectly with pliosaur tooth patterns, revealing a marine ecosystem where even the most perfectly adapted swimmers weren't safe from predation. The arrival of mosasaurs during the Cretaceous period added yet another layer of complexity to these already intricate marine ecosystems. Unlike the ichthyosaurs and plesiosaurs, which had been refining their aquatic adaptations for over 100 million years, mosasaurs burst onto the scene with evolutionary innovations that were entirely unprecedented. Their success story represents one of the most rapid and dramatic adaptive radiations in the history of marine life. What made mosasaurs particularly dangerous was their combination of size, speed, and intelligence. These weren't just large marine predators. They were sophisticated hunters with brain-to-body ratios that approached those of modern marine mammals. Fossil evidence suggests that mosasaurs possessed well-developed sensory systems that allowed them to detect prey through multiple channels simultaneously. They could track chemical trails through the water like marine bloodhounds, detect minute pressure changes caused by swimming prey, and even sense the electrical fields generated by the muscle contractions of other animals. The largest mosasaur species, such as Tylosaurus and Mosasaurus hoffmanni, grew to lengths exceeding 17 meters and possessed skulls over 1.8 meters long. But unlike the crushing jaws of pliosaurs, mosasaur skulls were designed for a different kind of predatory efficiency. Their teeth were sharp, recurved, and perfectly shaped for slicing through flesh and bone. More importantly, their jaw joints were incredibly flexible, allowing them to dislocate their jaws like modern snakes and swallow prey much larger than their head size would normally permit. This feeding adaptation opened up entirely new predatory opportunities. Mosasaurs could tackle prey that was previously too large for marine predators to handle effectively. Fossil evidence shows that they regularly preyed on sea turtles over a meter in length, large marine birds, and even other mosasaurs. Some specimens have been found with the remains of multiple large prey items in their stomachs, suggesting feeding frenzies that would have turned ancient seas red with blood. The geographic distribution of mosasaur fossils reveals just how successful these marine reptiles became. Within a relatively short evolutionary time span, mosasaurs had colonized every major ocean system on the planet. Their fossils have been found on every continent, including Antarctica, demonstrating their ability to adapt to a wide range of marine environments and climate conditions. This global distribution suggests that mosasaurs were not only formidable predators, but also exceptional long-distance travelers capable of crossing vast oceanic barriers. But perhaps the most remarkable aspect of mosasaur biology was their reproductive strategy. Unlike ichthyosaurs and plesiosaurs, which gave birth to single large offspring, some mosasaur species evolved the ability to produce multiple young simultaneously. Fossil evidence from pregnant mosasaur specimens reveals that certain species could carry up to 4 developing embryos at once, each already over a meter long at birth. This reproductive strategy allowed mosasaur populations to expand rapidly and colonize new marine territories with unprecedented speed. The evolutionary success of marine reptiles during the Mesozoic era created ocean ecosystems that operated on scales difficult for us to comprehend today. The biomass of large marine predators in ancient seas far exceeded anything found in modern oceans. Estimates suggest that the total weight of marine reptiles in some Mesozoic ocean regions may have been 10 times greater than the combined weight of all large marine predators in the same areas today. This abundance of large predators had cascading effects throughout entire marine ecosystems. The constant predation pressure drove the evolution of increasingly sophisticated defense mechanisms among prey species. Ammonites developed shells with complex internal structures that could withstand enormous crushing forces. Fish evolved schooling behaviors and burst swimming speeds that allowed them to escape even the fastest marine reptile predators. Even microscopic marine organisms developed new defensive strategies in response to the feeding activities of filter-feeding marine reptiles. The interaction between different marine reptile groups also created complex ecological relationships that had no modern equivalents. Fossil evidence suggests that different species sometimes engaged in cooperative hunting behaviors, with smaller, more agile predators driving prey toward larger ambush predators. Other fossils reveal evidence of interspecific competition, with bite marks and healed wounds showing that marine reptiles regularly engaged in combat with members of other species over territory and resources. These ancient marine ecosystems also supported levels of diversity that seem almost impossible by modern standards. Individual fossil formations from the Mesozoic era have yielded remains of dozens of different marine reptile species, each with unique adaptations and ecological roles. Some formations contain fossils of over 30 different ichthyosaur species alone, representing a level of diversity within a single predator group that has no modern equivalent. The sophistication of these marine ecosystems extended beyond just the reptilian predators themselves. The prey species that supported these massive predator populations had evolved into equally remarkable forms. Ancient seas teemed with giant ammonites, whose shells reached diameters of over 2 meters. Massive belemnites, the bullet-shaped relatives of modern squid, grew to lengths exceeding 3 meters and possessed internal shells strong enough to withstand the crushing jaws of marine reptile predators. Fish species during this period achieved sizes and morphological complexity that wouldn't be seen again until the evolution of modern marine ecosystems millions of years later. Some ancient fish grew to lengths rivaling modern sharks, while others evolved elaborate defensive armor that made them nearly invulnerable to all but the most powerful marine reptile predators. The diversity of fish species in Mesozoic seas provided the foundation for the complex food webs that supported the incredible abundance of marine reptile predators. The fossil record also reveals evidence of seasonal migration patterns among marine reptiles that spanned entire ocean basins. Just as modern whales migrate thousands of kilometers between feeding and breeding grounds, some marine reptiles appear to have followed similar patterns on an even grander scale. Fossil distributions suggest that certain ichthyosaur and plesiosaur species may have migrated between polar and tropical seas on an annual basis, following seasonal changes in prey abundance and water temperature. These migration patterns created dynamic ecosystems that changed dramatically throughout the year. During certain seasons, specific ocean regions would have been packed with migrating marine reptiles, creating feeding frenzies and mating gatherings that transformed entire seas into churning masses of predatory activity. Other times of year, the same regions would have been relatively quiet, with only resident species maintaining the basic ecological structure of the marine ecosystem.